All right, today's lesson is 35, similar and congruent polygons. Today we're going to talk about characteristics for similar and congruent. We'll talk about proportionate sides, angle, angle, angle similarity, and side, side, side similarity. So the first topic is similar. If polygons are similar, that means they have the same shape. So A, B, and C have the same shape. D definitely has a longer and a shorter side, so D is not similar to A, B, and C. The way we write that mathematically, we would say triangle A is similar to triangle B, which is also similar to triangle C. Notice A, B, and C, they're different sizes. That doesn't matter. They have to have the same proportionality, the same shape. So that makes them similar. The squiggle, that little wave right there, means similar. That's the sign we use in math. If shapes are congruent, it means they have the same size and the same shape. I lost my eraser. So, if you can see triangle ABC and DEF are the same size and the same shape. This one's definitely bigger, so it's not congruent. So congruent has to have the same size and the same shape. The way we write this is we say triangle, and I'm purposely going to pick a different order for letters. I'm going to pick C, B, A. There's a special order here. C, B, A. If I want to say it's congruent to this triangle, I use an equal sign and a single wave above it. That means congruent. And then I have to start with the letter in this triangle that corresponds to the same angle in this triangle. So if I started with C here, I need to start with F because C and F are the same measurement. These are the ones that correspond. Then I went to B. That's the one that looks like a right angle. So I'm going to go to E in this triangle. And then I went to A last. So in this triangle, I'm going to go up to D. So notice corresponding angles are listed in the same order. So to denote that, C goes with F, B goes with E, and then D and A are the same measurement. And likewise for sides. So this side right here, AC, corresponds to DF. So I would write that like this. Check it. Is it written like this? AC, are they first and last? Here, are they first and last? Good. So then I wrote it in the right order. So always be careful of the order you write your letters. Similar polygons. We talked about they have to have the same shape, right? So part of that means they have the same measurement of angles. So look at these 4 polygons. They've all got 100s and 80s, but one of them definitely doesn't have the same shape, and that would be D. So D is not similar to the others. But another requirement for similar polygons is the sides must be proportionate. So visually it looks like they're proportionate, it looks similar, but we're going to test that mathematically to see if there's a ratio that is proportionate to each other. So let's try A and B and see, are they similar? So we're going to go short side to long side, short side to long side. We're going to set up a ratio. 8 over 12, that's that ratio. Is it equal to this ratio, 6 to 8? This is the proportion we're checking. We're going to put a question mark. Is 8 over 12 equal to 6 over 8? Let's do a cross multiply check. Is 8 times 8 equal to 12 times 6? No, it's not. So therefore, these two, we're going to put the similar is not, okay, not similar. We're going to do the same test for these two. We're going to check these guys. Put a question mark. Are they similar? So let's build another proportion. Let's go short to long, 8 to 12. Is that proportionate to or equal to this short to long side, 4 to 6? And let's put a question mark. That's what we're checking. So I would do another check, maybe without cross multiplying, just to show you another way. Is there a relationship going vertically or horizontally? Look at this vertical relationship. If I look at a 4 to a 6, I could go, well, half of 4 is 2. I could add that on and get a 6. Is half of 8 would be 4, and add that on to get a 12. Yeah, that actually has the same relationship. What about going across? If I double 4 to get an 8, if I double 6 to get a 12, it's the same doubling. One more check, cross multiply. 6 times 8 is 48. 12 times 4 is 48. 48 equals 48. So I know these two, their ratios equal each other. They're proportionate. So these two are similar. And I don't have to worry about this one. Could these two be similar? No, because these are not similar. These are similar, so there's no way these could be similar. Okay. Congruent polygons have the same angle measurement and the same side measurement. We're going to talk about side, side, side similarity. If two triangles have proportionate corresponding side lengths, then they must be similar. So we already talked about similar triangles have proportionate sides. We're going to go in reverse. If sides are proportionate, then the triangles are similar. So let's test to find out, to see if they're similar. We're going to test, are the sides proportionate? So let's do, I'm going to randomly pick this 5 and this 8, make a ratio out of it. Is that proportionate to 12 and 18? 12 and 18. Do a question mark there, that's what we're checking. Let's cross multiply and check, because I don't see an easy integer relationship. Well, I guess I could check down, but we're going to go cross. 5 times 18, does that equal 8 times 12? So I went across and across. 5 times 18 is 90, and 8 times 12 is 96.
Mrs. Burke, please come to the front office. Mrs. Burke to the
Not
front
equal.
office.
So these are not similar. All right, so next we're going to talk about angle, angle, angle similarity. So likewise, if the angles are congruent in two triangles, then they must be similar. Okay, that's as much as we can assume if all we know is their angles are congruent. So if I said this was 55, maybe this is 65 and this is 60, maybe this one's 60, 65, 55, it just is blown up. If the angles are all the same, then we can say they are similar by angle, angle, angle. And how does this help us if we know proportionality with similar triangles? Well, one cool thing about that is you can find missing side lengths. So look at this triangle. We know it's a 3, 4, 5. This one's a 9, question mark, 15. So if we know they're similar, we can set up a proportion to find the missing side length. So I'm going to pick a pair of sides on each one that correspond to each other. So I'm going to make a proportion with 3 and 4. And I'm going to set up an equality or a proportionality with 9 and x. 9 and x. So again, I went shorter to longer, shorter to we don't know, but it's the corresponding parts. And then I'm going to set up a cross multiply here and say 3 times x, again I went 3 and x, equals 4 times 9. I'm going to solve that. 3x equals 36. 4 times 9 is 36. And then to find x, I go, well, 3 times what would be 36? I'm going to divide by 3, divide by 3. X would give me 12. Put a 12 right here, and does it look about right? Is this one a little bit bigger than the 3? This is a little bit bigger than the 9, and it's proportionate. So that's how we find our missing side length. We're going to throw some units on there, inches. And here's another application of proportionality. Say if you went to a hobby store and you bought a model airplane. On the box it'll say this model airplane is a 1 to 24 scale. What that means is for every inch on your model, it would represent 24 inches in real life. So that wheel or that wing or that propeller, it's going to be 1/24 the real life size. So that scale factor, in this case, we could say in a drawing, 1 inch is going to represent 4 feet in real life. So 1 inch is 4 feet. The question is, what is the length and width of a room that is 5 inches by 4 inches in the drawing? So you've got a rectangle here. It's a 4 by 5. And then in real life, let's put the units here. In real life, what is the amount of feet? So take each inch. If this one has 4 inches, I'm going to divide that up into inches. So this would be an inch, which would represent 4 feet. This inch would represent 4 feet. This one represents 4 feet. And this one represents 4 feet. So really, altogether, I have 4 times 4, or 16 feet in real life. And I could do the same thing here. What did I do? I just times by 4. So here I'm going to times by 4. to get 20 feet. So that would be the length and width of a room in real life if my drawing was proportionately shrunk or proportionally sized down. I'm just going to multiply by that scale factor of 4 feet. So there's a good application. Okay, and that's the end of the lesson. You can do practice problems on 233.